Now, since we have gone through the basics, how to write Verilog, we have written a lot of Verilog code, and we have written a few test benches as well. Let's now understand how do you write a test plan and self-checking test bench. What do I mean by that is, so whenever you're writing a Verilog code, it's not only important to just write a Verilog code and check in one scenario. You want to make sure all possible scenarios are tested, and you can't manually test it. So you need to write your test bench in such a way that it's automatically checked and gives a pass or a fail results. So let's understand how that is done. Before we do that, let's go to our favorite basic example. So this is a counter which we have designed. It's a simple counter. It's a 4-bit counter. At the reset is active high, it goes to 0. And if enable is 1 on the clock edge, count increases by 1. So let's see how to write a simple test plan for this. And we're going to write a very basic test plan just to understand the concept. So let's see what is the test plan for this. So first thing is, there is a reset in this counter, and what is happening on that reset is, at reset, when reset is equal to 1, count should go to a value 0. So that needs to be tested. Even though it's very clear from the code, sometimes when multiple blocks are compiled, it may not be very clear. So it's very important to write these test plan and create test cases for it. Then second is, at the clock edge, if enable is 1, the count should increase by 1. So if enable is 1, then count should increase by 1. This needs to be tested. So we'll write a test case for that. If enable clock edge, if enable is 0, then count should not increase. Okay, so then count should not increase. So this creates our basic test plan in terms of what we want to test in this counter. That at reset, which is value 1, active high reset, it should go to value 0. When enable is 1, count should increase by 1. And if enable is 0, count should not increase by 1 and stay at the same value. So now let's understand how do you write this test bench. So first important thing is, of course, you will instantiate your counter. Then you will have an initial loop to set up all the DUT signals which you are using to set. Clock is set to 0, reset is set to 0, enable is set to 0. We are introducing a signal set which says, okay, whether there was an error or not. Then we are creating our clock with 10 time units. And of course, we are saving our files in the waveform for if we want to debug something later. And we have also introduced a signal called terminate sim, which basically will terminate the simulation. And if DUT has any error, in the log file, it will print passed. If the DUT does not have any error, that means DUT error count is 0, then in the log file, it will print pass. Otherwise, it will print fail. And this is very important, right? Then after that, you can group or grep through these files to see which test fail. So this all can be then automated using script. So this is an important aspect of your test plan, that after test plan is made, you should be able to automatically verify, maybe create a dashboard, what passed, what failed. So it's important part of writing a self-checking test bench. Then we have created an initial block where what we are doing is we are applying reset and then coming out of reset. So applying reset, since it's active high, means changing reset to 1, and then coming out of reset means changing reset to 0. And then basically we are also changing enable, changing it to 1, changing it to 0. So we are making sure all when enable is 1, the count will increase, and when enable is 0, the count will decrease. So we have created a count underscore compare. Okay, this basically is what we are expecting our count value to be. Think of it this way, right? Typically, a person who's gonna write test bench or doing verification will be a different person than person who has written the RTL code, and they both will be reading the spec and creating their test bench accordingly. So one person, basically RTL engineer, will be reading the spec and creating their code, and then basically verification engineer will creating their test bench code. but both are going by the interpretation of spec. So in this simple case, the interpretation of spec may not be very different, but in any general case, the interpretation can be different. So basically, both are writing from their understanding. So what the expected value of certain signals and output should be. So basically, we are writing here, okay, count at reset should be 0, and if enable is equal to 1, count should be increased by 1. So this is the count, and what we'll check is if count compare with what we are expecting count value to be versus what is coming out of DUT, then basically there is an error. There is an expected value of something which is count compare, but we are getting a value count which is not an expected value, and then we will issue a signal DUT error, and when the simulation terminates, as we saw, DUT error will accordingly put pass or fail. Now this may look trivial for a simple case, but as I said, right, specs can be complicated, their interpretation can be different, and also there can be real bugs in the design itself, and the whole goal of test plan and writing test bench is to catch those bugs. So these paths are available. I'll be sharing the path so that you can go through your next test plan exercises.